Hello everyone and welcome to my presentation. First of all, let me thank you for watching this presentation and the P0SCon conference for allowing us to talk about our research. Today I'm here to talk about data integrity and vulnerability in the aviation industry. Let's talk about vulnerability we discovered in flight management systems. Let me briefly introduce myself. I'm Dadgar. I'm working as a red teamer. My other colleagues are in this research are Reza Dorosti, a reverse engineer, and Reza Zamiri, a security researcher. Okay, a little disclaimer. All the content shown in this presentation is entirely legal and is strictly for educational purposes only. We will not be responsible for any illegal use of the materials. The vulnerability we discussed in this presentation are reported to the owner company and fixed already. Okay, reporting timeline. As you can see in the reporting timeline, we discovered the vulnerability in August 2018, and we started a reporting process with the owner company Honeywell. Honeywell is a famous company in the aviation industry. After months, in January of 20, they said, we have issued mitigation and notified our customers. Honeywell added our names to the security researchers list, but after that, they didn't answer our emails. After the talk, there'll be time for discussion in the question and answer section. Okay, let's go talk about some backgrounds and concepts we need to know about aircraft navigation systems and data integrity and how avionics can cause risk for flights. What is avionics? Avionics is a literal blend of terms aviation and electronics. Avionics is a category of electronic systems and equipment specifically designed for use in aviation. The avionics installed in an aircraft or spacecraft can include engine controls, flight control systems, navigation, communication, flight recorders, lighting systems, electro-optic systems, weather radar, performance monitors, and systems that carry out hundreds of other mission and flight management tasks. Every modern aircraft, spacecraft, or satellite uses electronic systems of varying types to perform a range of functions pertinent to their purpose and mission. Next slide is about flight management system. A flight management system, or FMS, is a fundamental component of a modern airliner's avionics. In many ways, it's like the GPS in your car, with waypoints programmed in between the origin and the destination. You program in where you are going and off it goes. A primary function of FMS is in flight management of the flight plan. Using various sensors to determine the aircraft position, the FMS can guide the plane along with the flight plan. The FMS will allow the airplane to hook up the autopilot and maintaining the heading within a few feet. Typical flight management systems consist of three parts. A flight management computer, control display unit, which enables display and modification of various parameters, as well as allowing the flight crew to select the multiple FMS operating modes. And a data loader is one of its important components. A flight management computer is the heart of a flight management system, providing centralized control of navigation and performance management. The FMC accepts information from numerous navigation sensors, including VOR, distance measuring equipment, and GPS. Data from each sensor is prioritized based on its known percentage of error and blended to provide the most accurate position information. The flight management computer has a programmable database containing known radio navigation stations and their tunable frequencies, airports, seats, and stars in approach data for runways. Because of frequent changes, the database requires updating every 28 days. This is accomplished by loading electronic media file into some type of data loader, which can vary from a floppy drive or even a compact disk. In some cases, the data loader can be used to download diagnostic or fault data to the same type of electronic media from airplane. You can see one example of a data loader. The flight plan. The flight plan basically are documents filled by a pilot or flight dispatcher with the local air navigation service provider prior to departure, which indicates the plane's planned route or flight path. The flight plan is generally determined on the ground before departure, either by the pilot for a smaller aircraft or a professional dispatcher for airliners. It's entered into the FMS either by typing it in or selecting it from a saved library of common routes or via an ACARS data link with the airline dispatch center. ACARS is a radio data link. All FMS devices contain a navigation database. The navigation database contains the element from which the flight plan is constructed. These are defined via the ARINC standard. The navigation database is usually updated every 28 days to ensure that its contents are up to date. Each FMS contains only a subset of ARINC data relevant to the capabilities of the FMS. NDB elements. The NDB contains all of information required for building a flight plan or flight path, consisting of waypoints, airways, airport runways, and also standard instrument departure and terminal air wall, which in summary we call them seeds in the stars, that are procedures and checkpoints used to enter and leave the airway system by aircraft operating on IFR flight plans. The process. What's the process of uploading and updating NDB file? The airliners have to download NDB file updates from the website of FMS vendors. Then they will extract these NDB files using the specific software, and they will copy them into a floppy disk. After that, the technician will upload NDB files via the data loader to the FMC. The interesting point for us is that the FMC device has the capability of data integrity check and only accept NDB files which are not manipulated. Otherwise, the technician will face an error at the time of loading the NDB file. What we are going to do. From an offensive standpoint, one of the most likely attack vectors is to manipulate the NDB file, which is willing to be loaded on the FMC device. So the attacker will only need to bypass the data integrity check mechanism, and after that will be able to manipulate some information that is critical for a flight. Data integrity is the maintenance of and the assurance of the accuracy and consistency of data over its entire life cycle. Maintaining data integrity is a core focus of many enterprise security solutions. Data integrity can be compromised in several ways. Each time data is replicated or transferred, it should remain intact and unaltered between updates. Error checking methods and validation procedures are typically relied on to ensure the integrity of data that is transferred or reproduced without the intention of alteration. What is CRC? CRC, or Cyclic Redundancy Check, is an error detecting code. It finds changes in data as it travels from one computer to another by adding a code to the end of the data string. The sending computer creates the code and the receiving computer checks it. If the codes check out, the data is accurate. If the codes don't check out, the data is corrupt. Okay, so in the next slide is a real-world example. As you can see in the picture, on the left side, we can see the original message, which is going to be transmitted at the center. We have a generator polynomial, or CRC generator, which is a 4-bit. It's coming from the algorithm. It can be more bits based on the CRC algorithm. So the point here is that we should add 1 bit less than its actual length at the end of the original message. The original message should be divided by our CRC generator. But the division of polynomials differs from an integer division. The underlying arithmetic for CRC calculation is based on the XOR. The operation that I guess many of you have a previous knowledge about it. It's straightforward and the resulting bit evaluates to 1 if only one of the bits is set. Otherwise, when the numbers are the same, the result will be 0. Okay, so we will continue this operation till the end, and finally we have a checksum or check sequence that we should add to the end of the original message, and the data is ready to transfer. Okay, so on the right side, we'll see what will be happening at the receiver side. If you look, as we started here with some zeros and reached to the checksum. So here the receiver will start this checksum at the end of our message. And it must know the CRC generator. So it's the reverse process of our previous mathematical operation. It should reach 0, and this way we can ensure the data is not altered. The data integrity and legacy code, or legacy hardwares. I want to mention 3 items. Legacy systems are not good for development and hard for maintenance. For example, you cannot have a modern type of encryption or checksum because of low processing power or storage on legacy hardwares. When using legacy code or legacy hardware device, you cannot roll out updates immediately, sometimes because you need to apply change on all devices or all customers. Another problem is always there are unsupported device or hardware still in use out there. This is a good example about aviation. You can't change FMC devices on all airplanes all over the world. There is always plane that use the old version of FMC device. Okay, the scenario. After finding the CRC algorithm, we can implement the same thing on our side. The only step which is challenging is to understand the mathematical operation from reading the assembly code at the time of analyzing a CRC in a computer-based environment. After bypassing the data integrity check, it's time to complete the attack vector. If we ignore the infection process, the attacker only needs to look for specific NDB files and then manipulate critical data on airliner systems. And the next slide, the malware. In addition to a common malware attack against the aviation industry, malware that is specifically designed to target avionics systems could be very challenging. A malicious actor can make a malware to search for NDB files on a hard disk, on the systems of airliners, and manipulate specific data. Cyberkill chain. Here is the whole kill chain scenario. We can assume that the first step is done via common attack methods like phishing, email phishing or something. In the second step, the malware should be able to search the hard drive for the NDB file. In the second step, it's based on the specific NDB file format or file header. Then it's time to change some data on the navigation database and bypass the file integrity check. In the fourth step, the technician will copy the manipulated NDB file on the floppy disk. Then he or she will update the FMC device with this NDB file. Finally, the pilot will start flying with this altered NDB and will face some risk scenarios. Frankly speaking, it's not very clear what will happen. But we know that the data from FMS will be sent for many other avionics systems, and this could cause some malfunction and a challenge for the flight. Also, we know that the flying with manipulated FMS is not safe at all, since many real-life incidents originated from an offensive FMS data input errors. Let's move on to our research on the data integrity check of Honeywell's flight management system. Honeywell is the biggest FMS manufacturer, and its products can be found in every modern aircraft. We tried to understand the logic behind checking the file integrity process of Honeywell FMC devices. And the tools, the OneNow. OneNow tool is a desktop application that interprets the binary data format used by Honeywell FMS, and by using this tool, we can see inside of a navigation database. OneNow has a wide capability to decode various formats of navigation database produced by Honeywell. Using OneNow, we can perform compare, export, archive, plot the NavDB content, and create loadable media for Honeywell FMS. So after some research, we investigated that the Honeywell is using a CRC algorithm for its file integrity check. If we consider the OneNow as the sender, the FMC will be the receiver. Both the sender and receiver should use the same CRC generator and CRC algorithm. By reverse engineering the OneNow software, by reverse engineering the NDB file inside the OneNow software. Finally, we managed to detect the routine which is responsible for calculating the CRC. As you can see, the scenario is you find out how CRC is calculated and checked. On the other side, when you apply a change on the data, doesn't matter a bit or a whole file, you need to patch a CRC. And after that, the FMS device will verify your manipulated database. In the next slide, I put a demo video of changing data on NDB file and patch CRC again. As I mentioned before, this is not only a weakness in the computer software. If we can bypass the CRC algorithm in the OneNow software, it must be possible to do it on the real FMC device. Thanks to our flight engineer friend, we have a picture of our NDB file loaded on a real FMC device on a real airplane. And the final part of this research is malware, which can target the NDB files and the flight management systems. I prepared the demo for malware,